As Loran C was due to be closed down in 2010, it has been withdrawn from the post-NPA 25 EASA ATPL learning objectives, and no questions on it should appear in examinations following that syllabus. However, because this course may be followed by those taking pre-NPA 25 courses, a short lesson covering some essential examination points is included as part of this course. Interestingly, there is a strong argument being made for an enhanced version of Loran, called eLoran, to become a backup for GNSS. Loran uses a strong signal, which is difficult to jam, and Loran is an independent, dissimilar and complementary system to other forms of electronic navigation, which helps ensure availability of navigation signals. The UK Department for Transport, via the General Lighthouse Authority, awarded a 15-year contract to provide a state-of-the-art eLoran service to improve the safety of mariners in the UK and Western Europe. Loran is an acronym for Long-Range Navigation. It is a system which is not global in its coverage. Loran C is a hyperbolic system, operating at a frequency of around 100 kHz. It uses the principle of differential range by pulse techniques to measure the time difference between the arrival at an aircraft's receiver of a series of pulses from a master transmitter and a series of pulses from up to 4 slave or secondary transmitters. This arrangement of transmitters is known as a chain. Loran C was planned to be shut down by the end of 2008, and the US Coast Guard shut its stations down in 2010. Airliners have largely stopped using it. However, the latest equipment has receivers that can evaluate simultaneously up to 8 slaves from 4 chains, presented as a latitude and longitude position. The chains and stations are acquired and deselected as required as the aircraft progresses through its waypoints. These Loran systems also possess powerful computers, which store and display useful navigation and performance data, and can interface with GPS or INS to provide FMS RNAV systems. The principle of operation is differential range by pulse technique. Let's look at the arrangement of a master and slave transmitter with a line joining them, called a baseline. The master transmits a pulse omnidirectionally, and this pulse is received a short time later at the slave station. The reception of this master pulse triggers the slave to transmit a pulse of its own, also omnidirectionally, but only after a fixed time delay. The difference between the time of reception of the two signals creates a series of hyperbole. If the receiver can measure the time difference, the aircraft's position is identified as being on a specific line. Clearly, in order to fix the aircraft's position, a second position line is required from a second slave transmitter. The frequencies used are between 90 and 110 kHz. This puts them in the LF band. Depending on the propagation characteristics of the atmosphere and the range, this may result in surface waves or sky waves. Surface waves are more accurate. Their error depends on range, but is only 1 nautical mile at 1,000 miles. Sky wave accuracy is quoted as 20 nautical miles at a range of 2,500 miles. In this lesson, we have seen that Loran works on the principle of differential range by pulse technique. The system is not global. It may be used over specified areas where a chain of transmitters still exists. These may be over land or sea. It operates in the low frequency band of 100 kHz. Surface waves give a range of up to 1,000 nautical miles with an accuracy of 1 nautical mile, while sky waves may give a signal of up to 2,500 nautical miles, but are only accurate to 20 nautical miles.